welcome to the course Fundamentals of Manufacturing Processes. In week 8 we'll talk about material removal, and this course is offered by Professor D.K. Dwivedi from Department of Mechanical and Industrial Engineering, IIT Roorkee. I'm your TA Alka Jangir from IIT Kanpur. So firstly we'll be going through some sample assignment questions which will help you in solving your weekly assignments, and then we'll go through some lecture notes. So first question is machining with reference to finishing purpose, the parameters best suited as. Your options are higher feed and depth of cut and low cutting velocity, and other option is lower feed and depth of cut and higher cutting velocity, or low depth of cut, feed and cutting velocity, or all of these high depth of cut, feed and cutting velocity. So the answer for the finishing operation will be second one. So what happens in finishing? You require finished surface, so a surface with very less roughness. So for that you always use lower feed rate and lower depth of cut but higher cutting velocity. Okay, so finishing uses slower feed rates and shallower cuts to maintain high precision and surface quality, and a lower feed rate is typically used for finishing operations in machining to achieve a better surface finish. A coarse feed rate is used for rough cutting, which removes excess material quickly and doesn't focus on surface finish. Feed rate of 0.01 to 0.05 mm per revolution is typically used for finishing operations. Now this is what your, in case of lathe machine or some finishing operations, your tool and your sample looks like. So this is the stock, so its diameter is being reduced. So let me use pointer. So this depth, it is the depth of cut. This will be lower, and also the feed will be the per revolution. What is the travel distance for this tool for per revolution in this y-axis? That will be your feet, and cutting velocity, this will be revolutions per unit time. Okay, so next question is, in the machining operation the shear angle is 45 degree and the rack angle is 10 degree. So calculate the value of shear strain. Your options are 1.7, 1.7 and 2. So for calculating shear strain, you have here answer will be 1.7. in the formula that is used is tan phi minus alpha plus cot phi. So here this phi is the shear angle and alpha is the rack angle, and these both angles are already given, so you have to just put these values in this formula. So 45 minus tan will be, and this will be the tan theta, and cot theta will be cot 45. Okay, so tan 35 plus cot 45 will be 1.7. And in case of the shearing operation, okay, here in this one is your tool and this is the chip that is formed after finishing. Okay, so this chip, it will be making a particular angle with this, and there is an angle to this horizontal one. This will be your shear angle, and the rack angle will be in between this tool versus this perpendicular angle. Okay, so shear strain in machining can be computed from the following equation based on the preceding parallel plate model. So gamma, which is your shear strain, will be equal to tan phi minus alpha plus cot phi. So here gamma is the shear strain, phi is shear plane angle, and alpha is rack angle of cutting tool. Then here for this equation, high shear strains are associated with low shear angles and rack angles, and shear strain of phi or higher have been observed in actual cutting operations. Thus, compared with forming and shaping processes, the material undergoes greater deformation. Now in this one, here you can see that if this tool will be at the 90-degree, that will be orthogonal type of machining, and if it is at an angle, that will be oblique. Here you can see various parameters that are given here. So thickness of chip formed, there is shear angle, rack angle, there is velocity that is related to the tool travel, and this is the workpiece. Next question is, which of the following is not true about the tool material used in cutting and machining? Your options are: it shall possess a high coefficient of friction, it shall possess high hot hardness, it shall possess a high thermal conductivity, or it shall possess a high wear resistance. So which one is not true? So in case of your tool material, it should have low coefficient of friction, so that there is less friction in between tool and your specimen, so that there is less wear of the tool. So first one is the incorrect one. Okay, so cutting tool materials, they should be harder and stronger than the material that is being cut or finished, and it is tough to resist shock loads, so it should have appropriate toughness, and it also should be resistant to abrasion, thus contributing to longer tool life. It should also have low erosion and corrosion rates, and it should also have good machinability. Okay, so that you can machine it in form of a tool. If it's very brittle, then it might lead to poor machinability, hence it will be very brittle as well. Now the coefficient of friction, so for the cutting tool material, it should be low, so that there will be no friction between the tool and the chip, or between the tool and the workpiece. And if the friction is high between the tool and the chip, then the chips will stick to the tool, and this will affect the quality of the machining process. Okay, so next question is the deformation caused by the relative motion of the tool and workpiece, and your options are plastic deformation only, elastic deformation only, plastic deformation in the nearby zone, and elastic deformation in faraway zone, and none of the above. So in case of cutting, you can picture or imagine like how cutting operation will take place. So near the tool, you will be having a zone which will be having primarily plastic deformation, while as you move far away from the tool, then you will be having elastic deformation. Okay, so third will be the correct option, and the explanation is, it can be seen in this image. Okay, so there are three types of zones that are there in case of this operation. So during material removal. So this is the tool, and tool, between tool and chip you will be having secondary deformation zone. In this part you will be having mainly plastic deformation, sticking and sliding friction, and heat generation. And in between chip and the workpiece you will be having primary deformation zone. In this part you have both elastoplastic deformation and here heat generation as well. In between tool and workpiece we have tertiary deformation zone. This one has elastic deformation which has friction and heat generation. So primary, secondary and tertiary, these are zones dependent on the heat that is generated in these zones. Next question is, in the orthogonal machining operation the cutting force is 850 Newton and the thrust force is 500 Newton. You have to calculate chip shear force with the given shear angle of 35 degree, and your options are between 409 Newton, 630 Newton, 450 Newton or 720 Newton. So the correct answer will be first one. Okay, so the formula for shear force is given as Fs equals to Fc multiplied by cos phi minus Ft times the sin phi. So here Fc is your cutting force and Ft is thrust force. So both of these values are given, and shear angle phi is also given 35. So you have to just put these values. So 850 times cos 35 minus 500 times sin 35, and the correct answer will be 409.45 Newton. And these forces, how these can be seen in the specimen. So here Fc will be in this direction, Ft is thrust force, it will be in this direction, and there will be R double prime which is the resultant force. Okay, so these forces such as friction force, normal force to the friction force, and then Fs, Fn, these shear force and normal to the shear force, these cannot be directly measured. So these are given in terms of cutting force and this cutting force and thrust force, which can be calculated. These are all given in these terms, and also shear, this angle, shear angle. Okay, so forces acting on the tool that can be measured are cutting force and thrust force. So all formulas are given in terms of these two forces. Next question is, which condition is known favorable for continuous chips? Your options are low feed and depth of cut, brittle workpiece, high speed, high back rack angle. So which one answer would be brittle workpiece? Okay, so there are three types of chips, that are discontinuous chips and continuous chips, and also there are continuous chips with built up edges. Okay, so in case of discontinuous chips, these are formed during machining of brittle materials and while machining ductile materials at lower speeds. And favorable conditions for these are brittle workpiece. So if your workpiece that you are working on, if it's brittle, then it is more likely to give you discontinuous chips. Slow speed of cutting, small rack angle, and large depth of cut. These factors also are more likely to give you discontinuous types of chips. Continuous chips, these are formed during machining of ductile materials at high speed, and these are favorable conditions for this type of chip to be formed are as follows. So if you have material that is ductile material such as aluminum, tin and other metals, copper, bronze. These are ductile materials, and if we have used larger rack angle, and if there is high cutting speed that is used, and low depth of cut, and proper use of coolant and lubrication, these all might lead to formation of continuous chips. Benefits of continuous chips: so this gives high surface finish. So as we saw in one of the after, I think during lecture notes we'll see why these continuous chips are helpful in case of having high surface finish. Okay, I think I can find it. Okay, so here it is. Okay, so if you have discontinuous chips, then it is more likely to have irregular surface due to chip discontinuities, and if it is continuous chip, then it is more likely to left good surface finish. Okay, and other benefit is that it will lead to high tool life, and it will have low power consumption. Next is continuous chips with build-up edges. These are the types of chips that are formed during the machining of ductile material at medium cutting speed, and favorable conditions for this are ductile material, also high friction at the face of the tool, lack of the coolant and lubricant. So these all conditions might lead to formation of continuous chips with build-up edges. Next question is the reason for the formation of crater wear on the surface of the cutting tool is. The options are: the strength of the tool is the lowest in this region, temperature is maximum due to the rubbing of chips with the rack face of the tool, lack of cutting fluid penetration, and surface irregularities were dominant in that area and leading to the formation of crater wear. So the answer will be temperature is maximum due to the rubbing of chips with the rake face of the tool. Okay, so the high temperature from rubbing chips against the rake face of a cutting tool is a major factor in the formation of crater wear, and some other factors are abrasion, which is the micro level abrasive particles which break off from the tool and workpiece during chip formation. They cause abrasion. Diffusion and decomposition. So at higher cutting speeds, the heat from the chips decomposes the tungsten carbide grains in the substrate, allowing carbon to leach into the chips. In case of plastic deformation, at high temperature, fine grained tools can undergo plastic deformation, which contributes to crater formation. Hardness. So high temperatures can soften the surface of the cutting tool, making it more susceptible to aggressive abrasion. The crater wear is most commonly seen when machining ductile materials, and it occurs mainly on the nose, front and the side relief of faces of the cutting tool. And to reduce crater wear, you can select appropriate cutting parameters and use a coolant tool. The surface near the cutting edge should be hard enough to resist abrasion and chemically stable to prevent diffusion between the tool and the work material. Next question is chip formation is affected by. Your options are workpiece material, depth of cut, and cutting speed, or all of these. So answer will be all of these. Okay, so here is the formation of chip. There are primary zone, secondary zone, this is the tool, and this is the machined surface of workpiece. So chip formation and machining is affected by a number of factors, including machining material. So if you are using material which is very brittle, then it might also reduce the life of tool, and the what type of chip will be formed, that will also be affected. So whether the material is ductile or brittle. So as we saw earlier, if your material is ductile, it is more likely to form continuous type of chips, depending on what feed rate and what depth of cut you use. And if it's brittle, it's more likely to form discontinuous chips having a very rough surface finish. Next is machining process. So the type of machining process such as turning, milling and drilling, these also decide what type of chips will be formed. Next is cutting conditions. So the cutting speed, feed rate, depth of cut and friction forces, these all also decide what will be the chip formation, how chip will be formed. Tool geometry and condition. So the geometry and condition of the cutting tool will also decide. And lubrication and cooling, the use of lubricants and coolants. Workpiece temperature and hardness, the temperature and hardness of the workpiece. Tool material and coatings, so the material and coatings that are on cutting tool wear and sharpness, the wear and sharpness of cutting tool. The final shape, length, thickness and width of the chip is dependent on the cutting conditions, mesh quality and other factors. Next question is the mechanisms that are responsible for the crater wear of cutting tool is or are. Your options are abrasion, adhesion, diffusion or all of these. So as you can see in this particular tool, you can see this particular part shows crater wear, and before that you have tool wear. Okay, so and also possible fracture line. So what will be the reason for formation of this crater wear? Okay, so answer will be all of these. So crater wear is a type of tool wear which occurs on the rake face of a cutting tool, and it is usually near the cutting edge, and it's caused by a combination of abrasion and diffusion of decomposition. So these are firstly there is abrasion. So it will be due to formation of micro level abrasive particles which break off from the tool and workpiece during the chip formation. Diffusion, at higher cutting speeds, heat from the chips, they decompose the tungsten carbide grains in the substrate and the carbon leaches out into the chips. Next is the various mechanisms by which wearing action takes place are like adhesion wear, abrasion wear and diffusion wear. And crater wear is most commonly observed when machining ductile materials because of the continuous formation of chips. The crater wear generally doesn't impact tool quality unless it deforms the cutting surface. Next question is, with reference to the Taylor equation, the percentage of tool life changes when the cutting speed is reduced to half, and the values of n and c are given. C is the constant, n is the exponent. N is 0.4, c is 300. So your options are, there will be 300% increase, there will be 465% increase, or there will be 465% decrease, or 300% decrease. So the answer will be only in between about two options, because here from the question you can see, if you will be, when the cutting speed is reduced, so cutting speed is getting reduced, so it is more likely that your tool life will be increased. Okay, so there will be increase. So there are two options, first two options. So out of these, which one will be correct? That will be 465. So formula that you have to use is the Taylor equation, which is V times T and T to the power n is equals to constant. So here n is the exponent, so which is already given as 0.4. Constant is also given, but here as you are given, you have to find out the percentage change, so you don't require the value of constant. Okay, so here for the equation you can write V1 upon V2 equals to T2 upon T1 times n is 0.4. Okay, so after that you can calculate T2 upon T1, which will be equals to 2 to the power 2.4, because 0.4 power will go as 1 by 0.4 when you will be taking at the velocity side. Okay, so 2 power 2.5, this will be 5.65, and when you will be finding out percentage change, then you always know the formula that is used will be final value minus initial value divided by initial value. Okay, so here we have T2 upon T1, so here T2 upon T1 minus 1 will be also there. Okay, so 5.65 minus 1 will be 4.65. Okay, so here then after that you have to multiply it with 100, so it will be 465.65%, and their increase we already defined why it will be increased, so the correct answer will be 465.65% increase. Next question is, during the cutting of blank, there will be discontinuous chips will be formed. So your options are brittle material, ductile material, or any material at high cutting speed, or any material with a heavy coolant. So you can get discontinuous chips in both of the cases of brittle material and ductile material, and out of which condition is favorable for discontinuous chips, those you have to remember. So in case of high cutting speed, it was more likely to form discontinuous chips. So third will be the correct answer. Okay, so for discontinuous time, these are the favorable conditions. So in case of discontinuous type, you can have irregular size and shape of chips, which will be in case of work material which has brittle like grey cast iron. If it is regular size and shape, then work material with ductile but hard, having feet which is large, and tool rake which will be negative, cutting fluid absent or inadequate. Ductile material forms continuous chips. In case of discontinuous chips, your material will be brittle, there will be low cutting speeds and large feed and depth of cut, there will be small rake angle and high tool chip friction. In case of continuous chip, so there will be opposite of both of most of these. So from brittle to ductile, low cutting speeds to high cutting speeds, and large feed and depth of cut to the small feeds and depths, and there will be sharp cutting edge, there will be large rake angle compared to here when we had small rake angle in case of discontinuous chip, there will be low tool chip friction, there will be low to medium cutting speeds, there will be large feed and small rake angles. Okay, so after this we'll be going through lecture notes. So first chapter is mechanism of metal cutting. Okay, so firstly, what is machining? So machining can be defined as the subtractive process used to get desired shape, size and finish by removing surplus material in the form of chips by a cutting tool and by providing suitable relative motion between the workpiece and cutting tool. Cutting tool is the one that removes excess material through direct mechanical contact. So for example, this drill bit, or in case of lathe machine, the cutting tool, that will be the cutting tool that you are using. Machine tool will be the ones that are holding this cutting tool and providing, so it provides necessarily relative motion between the workpiece and the tool. Next is basics of shape generation by machining. So there are two relative motions that will be there. So in case of drill bit also, you can see it will be rotating. That will be one of the motions, and it will be, there will be a feed, so there will be a up and down motion as well to for the penetration of this drill bit inside your this material. So there are two motions that are occurring. So based on those, there are two relative motions between work and tool generally needed to produce surfaces. So first is cutting speed. It is line generated by it is called generatrix, and it is primary cutting motion. Second is feed speed. It is line generated by it is called directrix, and it is called secondary cutting motion. Okay, so these can be at the different angle, right? So cutting motion will be in the motion that is your rotation is taking place, and feed is in perpendicular direction in case of drilling. Okay, so there will be production of new surface, and these are the generatrix and directrix. Next is relative motion needed for various types of surface generation. So in case of cylindrical surface produced, you require both generatrix and directrix types of motions. And now machining processes are based on the angle between cutting edge and cutting velocity. So these are classified into two types: oblique machining and orthogonal machining. In case of oblique machining, you have cutting edge of the tool, it is inclined with the normal to the cutting velocity. Cutting edge of the tool is perpendicular to the direction of cutting velocity. In case of oblique machining, the cutting force acts along all the three directions, x, y and z axis. In case of orthogonal, your cutting forces act along x and z directions only. So here no cutting force will be there along y direction. Examples of oblique machining are turning, milling, drilling and shaping. And examples of orthogonal machining are swing, sawing, broaching and parting off of tube wall. Now these are the both of the oblique cutting and orthogonal cutting. So here it depends on the angles between this tool and the cutting direction. Now according to type of cutting tool, machining processes are of three types: using single point cutting tools, using multi-point cutting tools and using abrasive as cutting tools. In case of single point, you have these operations, machining operations that you can use, such as turning, facing, necking, parting off, boring, shaping, and planing. In case of multi-point, you have milling, drilling, reeving, knurling and tapping, hobbing and broaching and sewing. In case of abrasive as cutting tools, you have grinding, honing, lapping, super finishing, polishing and buffing. Second chapter is chip formation. In this case, firstly machine tool. So it is a power driven machine which performs some machining operations including grinding. So the functions in machining are: it holds the workpiece at a place, it positions tool relative to the work, and it provides power at speed, it provides feed, it provides depth that have been set. Okay, so this is how it's your tool. In between tool and chip there is particular angle in between these, that's alpha, and this is the chip that is formed. Okay, this is the undeformed or unmachined part, and this is the finished or machined part. So here the particular TC, that is thickness of the chip. Now in case of chip formation, you have shear zone in between chip and the undeformed part, and you have secondary shear zone in between chip and tool. Okay, so primary shear zone will be this, and in between this primary zone and the horizontal part you have effective shear angle. And chip formation is also influenced by the type of workpiece metal and also the cutting conditions. There are 4 types of chips: discontinuous chip, continuous chip with build-up edges, and serrated or segmented chips. Now in first you have discontinuous chips. Here these are the favorable conditions for formation of discontinuous chips. So these chips, they look like these ones, so there are discontinuity in the chip, so it won't be a continuous chip, continuous metal. Okay, and because of this discontinuity there is also irregular surface finish, so irregular surface due to the chip discontinuities. So this will be having brittle work materials, low cutting speeds and low feed and depth of cut, and it also has high tool chip friction. So if you are using a material that is brittle, so such as cast iron, these cast iron or high carbon steels, those will more likely to form discontinuous type of chips. And the lower cutting speeds and feed is also, if it's large and depth of cut is large, that will also form discontinuous chips. High tool chip friction, so in between tool and chip if the friction is higher, then it is more likely to form this discontinuous type of chips. Next you have continuous chips. So this will be a continuous type of metal. So it will occur in case of ductile materials, and it will be having high cutting speeds. So in case of high cutting speeds, it's more likely to form continuous chip. Next is small feeds and depths. This will also favor continuous type of chips. Sharp cutting edge for the tool, or low tool chip friction. So this low tool chip friction will depend on the friction in between tool and workpiece. So that depends on the materials of both tool and this workpiece, and also the lubricants that I used. So lubricants are used for reducing the friction. So if you are using appropriate lubricants, then it is more likely to form continuous chips, which will be advantageous. Next is continuous chips with build-up edges. So here, as it is shown, there are build-up edges and there are particles that are left because of build-up edges on the new surface. So the surface that is formed won't be as smooth as it will be in case of continuous chips. So this occurs in case of ductile materials and when there is low to medium cutting speeds that are used. Okay, so in previous one we were using high cutting speeds, but if there is ductile material but you are using low to medium cutting speeds, then it's more likely to form continuous chips with build up edges. Tool chip friction, it causes portions of chip to adhere to the rake face, and if this build up edges, they form and then breaks off cyclically. Okay, they keep on forming and they keep on breaking off. Next is segmented chips or serrated chips. So these are semi-continuous type of chips which are also, in case of appearance, they are sawtooth type of appearance. So here you have alternate high shear strain zone and low shear strain zone, and these have cyclical chip that forms with alternating high shear strain then low shear strain, and these are associated with difficult to machine metals at high cutting speeds. So it is mainly material dependent. Next chapter is material removal process, type of chips and power consumption. So in case of forces, so the all forces we can't measure, so the only forces that we can measure are the cutting force and the thrust force. So other forces that are there, they are given in the formulas are given in form of these cutting force and thrust force. Okay, so the friction force F, so from now on F is used as the friction force and normal force to the friction is capital N, and shear force is denoted as Fs and normal force to shear force is denoted as Fn. Okay, so and the vector addition of F and N will be known as capital R, which is resultant vector. Okay, and vector addition of Fs and Fn is resultant R dash. So the forces acting on the chip must be in balance and R dash must be equal, opposite and collinear with the capital R. Okay, so in case of tool, the forces that are working will be collinear with the forces that are acting in the workpiece. Okay, so it will be opposite in direction but collinear, equal and collinear. So F force, shear, this friction force and normal force, they are in case of tool, and the this shear force and normal force to shear, they are in workpiece, and this phi is again shear angle. Tool chip interface friction. So here coefficient of friction between tool and chip is given as this mu equals to F upon N. F was the again your friction force, N is normal force. Friction angle related to coefficient of friction can be given as mu equals to 10 beta. And shear force, it can be shear stress acting along the shear plane can be given as the S equals to Fs upon As. Fs is the shear force, As is the area of the shear plane. So this area can be given as the thickness times the width divided by sine phi. So phi is given here. This is the shear angle. Okay, so shear stress should be equals to shear strength of work material during cutting. So for the material to be cut, you require shear stress which should be equals to shear strength of work material. Next is measurable forces in orthogonal cutting. So as we saw earlier, this F and Fs and Fn, your friction force, normal force, shear force and normal to shear force, these cannot be directly measured, and so forces acting on tool that can be measured are cutting forces and thrust force. Okay, so all these formulas are given in terms of these two. Okay, so these can be calculated using measurable cutting forces using force equation. So here this friction force is Fc sin alpha plus Ft cos alpha, and capital N, this normal force is normal to the friction force is Fc cos alpha minus Ft sin alpha. Fs is the Fc cos phi, Ft sin phi, and Fn is Fc sin phi plus Ft cos phi. And based on these calculated forces, shear stress and coefficient of friction, they can be determined. Next is shear angle from the Merchant theory. Okay, so here chip thickness, shear angle, these are given. So the power that is consumed for the machining, so the power to perform machining can be computed from PC equals to Fc times nu. So here PC is cutting power, Fc is cutting force, and nu is cutting speed. And the gross power to operate the machine tool, Pg, is given by Pg equals to Pc upon E. Capital E is the mechanical efficiency of machine tool and typical E for the machine tools. So here E is the can be around 90% or below that. Okay, it can be around 90%. So when you will be dividing this PC by 0.9, then you will be getting a value which will be greater than the PC. Okay, so because of the poor efficiency, you will be having power, that required power, which will be higher than the power required for the cutting. Next chapter is heat generation. So there are three zones for the heat generation: primary zone, secondary zone and tertiary zone. In case of primary, you have chip workpiece interface. Secondary, you have chip tool interface. Tertiary, you have tool workpiece interface. Okay, so here from this image you can see in between chip and workpiece you have primary zone. Okay, primary deformation zone. In this part you have both elasto and plastic type of deformation and also heat generation. In case of secondary deformation zone, in between chip and tool you have plastic deformation which has sticking sliding type of friction and heat generation. In tertiary, in between tool and workpiece interface, you have tertiary deformation zone which has elastic deformation and friction and heat generation. Now for the cutting tool materials, these should be harder and stronger than the materials being cut, and it should be the material that you are using it should be harder and stronger than the material that you are cutting. So workpiece material, if it's aluminum, then the material that you are using for cutting as the cutting tool, it should have strength higher than the aluminum. It should be tough to resist shock loads. So if your material is very brittle and it has very less toughness, then it is more likely to break because of the shock loads. Next is it should be resistance to abrasion, thus contributing to long tool life. And it should have low erosion rate, and it should also have good machinability. Okay, so cutting tool material should possess these following quality. First, coefficient of friction, it should be low. So the coefficient of friction of the tool, cutting tool material, it should be low so that there will be no friction between tool and chip or between the tool and workpiece. And if the friction is high between the tool and the chip, then chips will stick to the tools, and this will affect the quality of the machining process. Toughness, so the property of to resist breakage due to the sudden load that results during metal cutting is termed as toughness, and this will reduce the breakage of the cutting edges of the tools. Next is cold hardness. So it is the amount of hardness possessed by a material at a normal temperature, and the hardness is the property by which it can cut, scratch other metals. And when the hardness increases, brittleness also increases, and a material which has too much of cold hardness is not suitable for the manufacture of cutting tools. Next is red or hot hardness. It is the ability of tool material to retain most of its cold hardness property even at very high temperatures, which while machining, the friction between the tool and the work causes heat to be generated, and the tool loses its hardness and its efficiency to cut diminishes. And if a tool maintains its cutting efficiency even at increased temperature during cutting, it can be said that it possesses red hardness property. So for example, in various in speed cutting steels, cobalt is added for red and hot hardness. So there are some alloying elements that are added for this particular property. Next is thermal conductivity. So thermal conductivity is the ability of a material to conduct heat, and the cutting tool should have high thermal conductivity to conduct heat away from the chip, tool and surface. So for if the heat doesn't dissipate and it remains there, then it can lead to reduction in the life of the cutting tool, as well as it can lead to deterioration in properties of the workpiece. So this heat should dissipate easily. Next is thermal stability. So thermal stability is defined as the ability of a material to resist breaking down under heat stress, and the thermal stability of the cutting tool should be high so that it wouldn't break down at high temperatures. Okay, so it should be thermally stable. Cost. So the cost of the cutting tools should be optimum. So some of the ceramic tools that are very costly, so some of the steels that are there, they are more cost effective compared to some of the ceramics. And also the ceramic tools are more likely to break because of the lower toughness. So one should not buy a cheap cutting tool and ruin the machining process. These cheap tools, they prove much costlier in the long run compared to those which have high initial cost but they cannot be operated for longer time at high speed. Next is wear resistance. So it is the ability of the cutting tools to resist wear due to adhesion and abrasion. Okay, so materials that are used for cutting tools, they should also have good wear resistance. Next chapter is tool failure and tool life. So the factors that affect tool life. So in case of cutting tool material, if its toughness and its hot hardness, these are two factors that affect the life of the cutting tool. And the choice of tool geometry, and based on such as the parameters such as cutting speed that will be used, depth of cut that will be used, and feed that will be used, these can also define the tool life. So in case of feed and depth of cut, so this is the feed. So if after one revolution, how much your tool is traveling in one particular revolution, that will be your feed. And the amount of feed, so if this feed is very high, then it is more likely to reduce the tool life. Okay, and the depth of cut is also, if it's kept very high, then it will more likely to reduce the tool life. High speed will also reduce the tool life. Next is mechanisms of tool wear. Okay, so these are the 5 mechanisms. So there can be abrasion, so and there can be adhesion, plastic deformation, diffusion, and chemical reactions that can be there between specimen, workpiece, and tool. In case of abrasion, the micro level abrasive particles that break off from the tool and workpiece during chip formation, they can cause abrasion. So in relative motion of the tool and the workpiece, in between that, if you have some of the chips that because of the high plastic deformation, they have work hardening, right? So the hardness of the even softer metals, it increases, so it can lead to wear of the tools. Diffusion and decomposition. So at high cutting speeds, the heat from the chips decomposes the tungsten carbide grains in the substrate, allowing carbon to leach into the chips. In case of plastic deformation, at high temperatures, fine grain tools, they can undergo plastic deformation, which contributes to crater deformation. And hardness, so high temperature can soften the surface of the cutting tool, making it more susceptible to aggressive abrasion. Next is Taylor's tool life equation. So it is V times capital T power N. So here equals to C. So V will be cutting speed in meter per minute. T is tool life, it's in minutes, and your constant N is a constant which is depends upon tool material, and capital C is the constant which depends upon the tool material and workpiece material and cutting conditions. Okay, that's it. That's it from my side. I'll go through questions once again. So in first question, your question was machining with reference to finishing purpose, the parameters best suited as. Your options are high feed and depth of cut and low cutting velocity. Second is lower feed and depth of cut and low cutting velocity and higher cutting velocity. Next is low depth of cut, feed and cutting velocity, and then high depth of cut, feed and cutting velocity. So answer will be second one. Okay, so in case of finishing operation, so you require very smooth surface. So finishing uses slower feed rate and shallower cuts to maintain high precision and surface quality. A lower feed rate is typically used for finishing operations in machining to achieve a better surface finish. A coarse feed rate is used for rough cutting, which removes excess material quickly and doesn't focus on surface finish. Feed rate of 0.01 and 0.05 mm per revolution is typically used for finishing operations. Next question is, in the machining operation, the shear angle is 45 degree and the rack angle is 10 degree. So you have to calculate the value of shear strain. So your options are 1.7, 1, 0.7 and 2. So answer will be 1.7. So for shear strain gamma, the formula is given as tan phi minus alpha plus cot phi. So here this phi is shear angle, alpha is the rack angle. Okay, so both of these are already given. So tan 45 minus tan, this tan 35 plus cot 45, it will be 1.5. And from this particular image, okay, you can see here, so in between chip and the horizontal line, it will be your shear plane, and the alpha will be rack angle between this perpendicular line and this tool angle that is made by the tool. So the shear strain in machining can be computed from the following equation based on preceding parallel plate model. So gamma is equals to tan phi minus alpha plus cot phi. Here gamma is shear strain, phi is shear plane angle and alpha is rack angle of cutting tool. Note from this equation that high shear strains are associated with low shear angles and rack angles. Shear strain of 5 or higher have been observed in actual cutting operations. Thus, compared with forming and shaping processes, the material undergoes greater deformation. Which of the following is not true about the tool material used in cutting and machining? Your options are: it shall possess a high coefficient of friction, it shall possess high hot hardness, it shall possess a high thermal conductivity, and it shall possess a high wear resistance. So the answer will be it shall possess a high coefficient of friction. So we can explain this by saying cutting tool material should be harder and stronger than the material being cut. It should be tough to resist shock loads. It should be resistant to abrasion, thus contributing to long tool life. It should also have low erosion rates. It should have good machinability. And in case of coefficient of friction, the coefficient of friction of cutting tool material, it should be low so that there will be no friction between the tool and the chip or between the tool and the workpiece. And if the friction is high between the tool and the chip, then chips will stick to the tool and this will affect the quality of the machining process. Fourth question is the deformation caused by the relative motion of the tool and workpiece. So your options are plastic deformation only, elastic deformation only, plastic deformation in the nearby zone, and elastic deformation in far away zones, or none of the above. So answer will be third one. So here in this image you can see there are three zones that are there. In case of primary deformation zone, you can see there is elastoplastic deformation and heat generation. In secondary zone there will be plastic deformation and also sticking sliding friction. In tertiary zone, in between tool and workpiece, there will be elastic deformation, and as you keep on going far from the cutting edge, so you will be having more elastic deformation compared to plastic part. Fifth question is, in the orthogonal machining operation, the cutting force is 850 Newton and the thrust force is 500 Newton. So you have to calculate the chip shear force with the given shear angle of 35 degree, and your options are 409 Newton, 630 Newton, 450 Newton, 720 Newton. Answer will be 409 Newton. So from this formula, in case of various formulas such as friction force and normal force, shear force and normal to the shear force, these cannot be directly measured. So the forces acting on tool that can be measured are cutting force and thrust force. So these are already given, and shear angle phi is also given, and the formula for shear force is given as Fc multiplied by cos phi minus Ft multiplied by sin phi. So Fc is cutting force, Ft is thrust force. So 850 multiplied by cos 35 and minus 500 multiplied by sin 35. So the answer will be 409.45 Newton. In next question, which condition is non-favorable for continuous chips? So your options are low feed and depth of cut, brittle workpiece, high speed and high wake angle. So answer will be brittle workpiece. So in case of brittle workpiece, there is more chances are more likely that it will be forming discontinuous type of chips. Okay, so in case of discontinuous chips, these are formed during machining of brittle material while machining ductile materials at low speeds. Okay, and favorable conditions for discontinuous chips are brittle workpiece, slow speed of cutting, small rake angle and large depth of cut. Okay, in case of continuous chips which are formed during machining of ductile materials at high speed, and these favorable conditions for this type of chip is to be formed are as follows. So it should have ductile material, large rake angle, high cutting speed, low depth of cut and proper use of coolant and lubricant. And benefits of having continuous chips are that it will give good and high surface finish, and it will have high tool life, and it will also have low power consumption. In case of continuous chips which can have build-up edges, so these type of chips are formed during the machining of ductile materials at medium cutting speed, and these have favorable conditions for this are ductile material and having high friction at the face of the tool, and there is lack of coolant and lubrication, so it will lead to high friction. Next question is the reason for the formation of crater wear on the surface of the cutting tool is. Your options are the strength of the tool is the lowest in this region, or temperature is maximum due to the rubbing of chips with the rake face of the tool, or lack of the cutting fluid penetration, or the surface irregularities were dominant in that area, leading to the formation of crater wear. So the answer will be second one. So the high temperature from rubbing chips against the rack face of a cutting tool is a major factor in the formation of crater wear. And these are some of the techniques which are responsible for the wear. So first is abrasion, which is the micro level abrasion particles which break off from the tool and also from workpiece during chip formation, which can cause abrasion. So these smaller chips, they have very high plastic deformation, leading to work hardening in these, which can lead to damage to the tool with very high hardness. Next is diffusion and decomposition. At higher cutting speeds, the heat from the chips decomposes the tungsten carbide grains in the substrate, allowing carbon to leach into the chips. Or plastic deformation, in this case at high temperatures, fine grained tools, they can undergo plastic deformation, which contributes to crater formation. Next is hardness. So in this case, high temperatures can soften the surface of the cutting tool, making it more susceptible to aggressive abrasion, and crater wear is most commonly seen when machining ductile materials, and it occurs mainly on the nose, front and side relief faces of the cutting tool. And to reduce crater wear, you can select appropriate cutting parameters and use a coated tool. The surface near the cutting edge should be hard enough to resist abrasion and chemically stable to prevent diffusion between the tool and the work material. Next question is, chip formation is affected by, your options are workpiece material, depth of cut, cutting speed, or all of these. So the answer will be all of these. Okay, so this is the formation of chip. So here your tool is moving in this particular direction and formation of chip is shown. This is a continuous type of chip, and this is the machined surface, and this is the primary shear zone in between chip and workpiece, and there is secondary zone between tool and chip. Okay, so chip formation and machining is affected by a number of factors such as machining material. So the material which is ductile or brittle, it will decide whether what type of chip will be formed. So it can be continuous and discontinuous based on what type of material is used. Next is machining process. The type of machining process such as turning, milling, drilling, so these will also decide what type of chips will be formed. Next is cutting condition. The cutting speed, feed rate, and depth of cut and friction force, these all will also decide chip formation. Okay, next is tool geometry and conditions. So geometry and condition of cutting tool, use of lubricants and coolants, the temperature and hardness of the workpiece, and the material and coatings of the cutting tool, and the wear and sharpness of the cutting tool, these all will decide, and these all will affect chip formation. The final shape, length, thickness and width of the chip is dependent on these cutting conditions and mesh quality and other factors. Next question is the mechanism responsible for the greater wear of the cutting tool are? Your options are abrasion, adhesion, diffusion, or all of these. So here in this tool you can see this part is belongs to crater wear and this here it is tool wear. So it is the depth edge of the tool wear. Okay, so one of the types of tool wear is crater wear. So in this case, which mechanism is responsible? Your options are abrasion, adhesion, diffusion, or all of these. So answer will be all of these. So crater wear is a type of tool wear which occurs on the rake face of a cutting tool and usually near the cutting edge. It's caused by a combination of abrasion and diffusion or decomposition. So in case of abrasion, there are micro level abrasive particles that break off from the tool and workpiece during chip formation, and in case of diffusion, at higher cutting speeds, heat from the chips they decomposes the tungsten carbide grains in the substrate and the carbon leaches into the chips. And the various mechanisms by which the wearing action takes place are like adhesion wear, abrasion wear, and diffusion wear. Crater wear is most commonly observed when machining ductile material because of the continuous formation of chips. The crater wear generally doesn't impact tool quality unless it deforms the cutting surface. Next question is, with reference to the Taylor equation, the percentage of tool life changes when the cutting speed is reduced to half. N is 0.4, C is 300. So your options are 300% increase, 465% increase, or 300% decrease and 465% decrease. So as we can see, cutting speed is reduced, so it will lead to improvement in tool life. So there will be answer will be from upper two options, and the Taylor equation is given as V t to the power n equals to constant. So from this you can get T1 upon T2 to the power 0.4 equals to V2 upon V1. So cutting speed is reduced to the half, so it will be 2 to the power 2.5 for T2 upon T1. Okay, so it will be 5.65, and the percentage change it can be given as end value upon start value minus 1 multiplied by 100. So T2 upon T1 is already there, so it will be 4.65 times 100. So it will be 465.65%. Next question is, during the cutting of blank, discontinuous chips are formed. The options are brittle materials, ductile materials, any material at a high cutting speed, or any material with a heavy coolant. So the answer will be any material at a high cutting speed. So you can get discontinuous chips in both type of materials, in brittle and ductile as well. So the factor that favors discontinuous type of chips is the high cutting speed, and heavy coolant doesn't support discontinuous chips. So in case of discontinuous type, so if it is of irregular size and shape, the work material will be brittle like grey cast iron, and if it is of regular size and shape, then work material ductile but hard, then feed will be large, tool rack will be negative, cutting fluid is absent or inadequate, and ductile materials they forms continuous type of chips. In case of discontinuous chips, these are the favorable factors. So the material will be brittle work material, and if cutting speed is also low, large feed and depth of cut, and small rack angle, and it can have high tool chip friction. So lubricant is also used, then it will lead to, if it's not used, then there will be high tool chip friction. Next is continuous chip. So in case of continuous chip, there is ductile work materials. They are more likely to form continuous chip, and the cutting speed used are high cutting speeds. Small feed and depths, and sharp cutting edge is used. Large rack angle is used. Low tool chip friction is used. Low to medium cutting speeds are used, and large feed, small rack angle is used. Then we went through lecture notes. So first, what is machining? So machining can be described as a subtractive type of process which is used to get desired shape, size and finish by removing surplus material in the form of chips by a cutting tool, and by providing suitable relative motion between the workpiece and cutting tool. Cutting tool is the one that removes the excess material through direct mechanical contact. So drill bit will be the cutting tool. Machine tool, it provides necessary relative motion between the work machine and tool. Now there are definitions for generatrix and directrix, and how depending on based on angle between cutting edge and cutting velocity, there are two types of machining processes: oblique machining, orthogonal machining. In oblique machining, you have cutting edge of tool is inclined with the normal to the cutting velocity. In case of orthogonal, you have cutting edge of the tool is perpendicular to the direction of cutting velocity. Cutting force acts along all three directions, while cutting force in case of orthogonal, it acts along x and z directions only. These are the examples that are given. Now, based on the contact between the tool and specimen, there are single point cutting tools, multi point cutting tools, abrasive type of cutting tools. Then chip formation. So machine tool is a power driven machine which performs a machining operation including grinding, and the functions in machining are: it holds the workpiece and the positions tool relative to work, and it provides power at speed, feed and depth that have been set. Now this is the assembly, and this is how chip forms. Then chip formation is, it's influenced by type of workpiece material. So if it's brittle or ductile, and cutting conditions, so what will be the feed rate and all those, they will also decide what will be the type of the chip that is formed. Now there are four types of chips: discontinuous chip, continuous chip, continuous chip with build up edges, serrated and segmented chip. So this is the discontinuous type of chip. In this, your material will be brittle, low cutting speeds, having large feed and depth of cut, having high tool to chip friction, and the surface finish will be not as good as continuous chip. In continuous chip, you have ductile type of materials for the workpiece, and there will be high cutting speeds that will be used. There will be small feeds and depths that will be used. There are sharp cutting edges, and there are low tool to chip friction. Continuous chips with build up edges. So in case of ductile materials, if there is a high friction in between tool and workpiece, so there will be low to medium cutting speeds. In this case you had high cutting speeds, here you have low to medium cutting speeds. And there is also tool chip friction causes portions of chip to adhere to the rack face, and this build up edges they form and then break off cyclically. Next is serrated chips. So in this case you have high shear strain zone and low shear strain zone, and these are alternate. So these are semi-continuous and they have sawtooth type of appearance. And the cyclical chip forms with alternating high shear strain than low shear strain, and it is associated with difficult to machine metals at high cutting speeds. Next is types of chips and power consumptions. So in this case you have various parameters. So friction force, normal force to friction, shear force, normal force to shear, and then there are resultant vectors, and then coefficient of friction is given and in terms of angle, and then shear force, which was Fs divided by As. As is simply area of shear plane, which is given as thickness times width divided by sine phi. And for cutting operation you require shear stress which is higher than shear strength of work material. And measurable forces, so these can be directly measured, so the only that can be measured are cutting force and thrust force. So all the formulas for these particular forces are given in terms of these, and with the help of sine alpha and sine cos alpha and sine cos phi. Power is given as the force times the cutting speed, cutting force times cutting speed, and the gross power is given by your cutting power divided by efficiency, and this efficiency can be around 90%. Then heat generation, so there are three zones: primary, secondary, tertiary. So in between tool and chip you have secondary deformation zone, in between chip and workpiece you have primary, in between tool and workpiece you have tertiary zone. And these are the various properties that are required for cutting tools. So it should have low coefficient of friction, it should have good toughness, it should have good cold hardness but not too much which can lead to brittleness. It should have good red or hot hardness, so even if the temperature increases for the tool it should retain its hardness. And it should have good thermal conductivity, thermal stability, cost and wear resistance. Its cost should be optimum. Okay, then we went through tool failure and tool life. So these are the factors that affect tool life. So the toughness and hot hardness of the material, and the geometric parameters are cutting speed, depth of cut and feed. And then these are the mechanisms of tool wear: abrasion, adhesion, plastic deformation and diffusion, and chemical reaction. And then we had Taylor's tool life equation, which we also used for solving some examples. Okay, so that's it from my side.